Good day everyone, my name is Sagayno Clarence. I'm from the SCP-41 and today I'm gonna discuss on 5 topics overall. Then the number 1 is about the CPU. Here is, or rather here's an example on what the CPU looks like. And I made a presentation or a document that is self-explanatory, so if we just continue reading, we could understand what it really means. So, number 1 is how the CPU works. The CPU, or the Central Processing Unit, is widely regarded as the core component of any computing system, meaning it is responsible for executing program instructions, processing data, and controlling the overall operation of the computer. Here's an example of a CPU, or a Central Processing Unit. Then every digital activity such as launching applications, typing documents, browsing the internet, or running simulations relies on the CPU performing with billions of microscopic operations per second with high accuracy and reliability. Then, at a fundamental level, the CPU operates using a structured process known as the fetch, decode, execute cycle, which means the CPU will first fetch the data, then decode it, then execute what the data says. So during the fetch phase, the CPU retrieves the next instruction from the main memory using the program PC, or program counter rather, which keeps track of the address of the current instruction. Then the instruction is transferred, so here is transferred to here into the instruction register, or IR. In the decode phase, well, that's how the fetch phase ends. And next is the decode phase in the cycle. So, in the decode phase, the control unit interprets the instruction, determining what operation is required and which hardware components must be activated. So, for example, if you want to boot up your PC, or if you want to press your mouse, a data is going to be fetched from the word fetch, as the cycle states. It will be fetched from that, then it will be executed or decoded, so that the hardware components knows that it's going to be used, or it must be activated. Then, during the execute phase, the arithmetic logic unit, or ALU, performs the required computation, such as arithmetic calculations, logical comparisons, or data movement. The result is then stored in a register or written back to memory. And then the program counter, or PC, advances to the next instruction. So, next is the CPU consists of several critical components. Registers are small but extremely fast storage locations that temporarily hold data and instructions currently being processed. The ALU, or Arithmetic Logical Unit, performs mathematical and logical operations, including addition, subtraction, comparison, and Boolean logic. Then, the control unit coordinates all the activities inside the processor by issuing control signals that synchronize operations. So CPU is as synchronized as a human being, or maybe more, because they follow instructions clearly. Then let's move on, because this next part is pretty pretty self-explanatory, and many people, I just want to say that many people think, or when they hear the word CPU, they think of the whole system unit in a computer, the whole where motherboard, heatsink, fan, GPUs are all located. It's called a system unit and not a CPU. Then For an example of the CPU or how the CPU operates, like I said earlier, when opening an application, performing a mathematical calculation, typing a keyboard, or pressing on a mouse, playing a video or a game, and multitasking operations. That is how the CPU works. Okay, let's move on. Then for the next topic, number 2, which is the evolution of the CPU, part 1 to 4, since there are 4 videos that I've used. Then I've summarized each and every video from the information that I found there, and I'm going to explain it. So here is a representation of the evolution of the CPU. Credits to the owner of this picture, which is the Intel. So this is how the Intel evolved throughout the years. From the first one is just a processor, something with many feet that is sticking out, so it's not that durable because the feet can be damaged because it's so out in the open. Then if we fast forward to the current, which is right here, the Intel Core i9 series, or the robot one, it's very advanced and very compact compared to the first one. So for the part 1, early computing machines and microprocessors. So the earliest electric computers were constructed using vacuum tubes, which were physically large, fragile, energy intensive, and produced significant heat. These limitations restricted computing efficiency and accessibility. So if you all are not aware, computers before were as large as a room, as a single room. Then its capabilities is not even comparable to the capabilities of a simple computer right in this generation. So the invention of transistors marked a major breakthrough by enabling smaller, more durable, and energy efficient machines. And as I've said, integrated circuits allow thousands of transistors to be embedded into a single silicon chip. So they've made it more durable, smaller, so that it could be stored easier, and overall greatly reducing the cost and size. Then the part 2 is growth on instruction sets and processing power. As microprocessors advanced, manufacturers focused on increasing clock speeds, expanding instruction sets, and improving data handling capabilities. Standardized architectures such as x86 enabled compatibility across generations of hardware and software platforms. Then, larger word size improved precision and allowed CPU to address larger memory spaces. This era introduced personal computers into households and educational institutions, making computing widely accessible. So this is the part where computers are now being applied, and it's the part where, or it's the era in which computers are being utilized properly because it's evolving. Then part 3 is the integration with operating systems. With the rise of advancing operating systems, or OS as we all know. Okay, for a great example of an OS is this. Okay, next is CPUs incorporated hardware mechanisms for multitasking, memory protection, and system security. Features such as interrupt handling, privilege levels, and virtual memory enabled efficient task scheduling and protection against unauthorized access and system crashes. This allowed multiple applications to operate concurrently without interfering with each other. So this era of the integration with operating systems enabled the computer to, simply put, multitask. efficiently, of course. Then last but not the least, part 4, performance optimization and modern architecture. Modern CPU employ sophisticated optimization techniques, including pipelining, cache hierarchies, branch prediction, and multi-core processing. These technologies maximize instruction throughput and minimize execution delays. Contemporary processors are capable of executing billions of instructions per second, while maintaining power efficiency and thermal stability. A good example here is a modern laptop processor can simultaneously run productivity software, multimedia applications, and background services without noticeable performance degradation. So it's said that even a modern laptop or a simple laptop in this modern generation can simultaneously run productivity software. For example, let's just say a programming software like a C or a Visual Studio, then open a multimedia applications or a simply Facebook or Chrome, some kind of browser, and background services, the applications that run on the background. Okay, that is it for the CPU. Moving on to the next topic, which is the overview of the GPU. GPU or graphics processing unit is here. Looks like that. That is a GeForce RTX, which is a very advanced GPU, by the way. Then it's a specialized processor optimized for highly parallel workloads. So this is very long, so I'm just gonna summarize it. So originally designed to accelerate graphics rendering, GPUs are now widely used for scientific simulations, artificial intelligence, video processing, and large-scale data computation. Unlike CPU, which prioritize sequential instruction and execution and control, GPUs contain thousands of smaller processing cores that operate simultaneously. So if your CPU is just giving out or it's very old and it's not that strong anymore, you can just simply get a GPU that is compatible with your motherboard, and you can run your computer better than before, or maybe as good as new, because GPU helps overall performance of the computer on whatever you want to do with it. So GPU efficiently processes large blocks of data by executing the same instruction across multiple data concurrently. This parallel architecture makes GPU particularly suitable for rendering images, applying graphical effects, and performing matrix-based calculations in machine learning algorithms. This is commonly found in gaming industry because gaming industry uses a lot of bits, and GPU makes rendering images very easy and very clarified. So it makes the screen look clearer and more clarified to the eye. The modern GPU also support programmable shaders, enabling developers to customize rendering behavior and optimize performance. So an example of this is, like I said earlier, in a video game environment. The GPU calculates lighting effects, textures, shadows, object rendering, while the CPU manages the game logic, artificial intelligence behavior, and input processing. So basically, if your CPU is alone or you do not have a GPU in a video game environment, your CPU and RAM will handle all of that stress. Just imagine it. How even the strongest CPU might be laggy if it handles this much workload simultaneously. But the GPU provides the extra layer of power, in which makes it possible for the CPU and GPU to work together. Then next is number 4, which is the SAP-1 operations. Okay, so SAP or SAP1 operations. Here is a table that consists of how the SAP operation operates simply. So The Simple as Possible Computer, or SAP, is an educational model designed to demonstrate fundamental principles of computer architecture and instruction execution. It provides a simplified yet functional representation of how a CPU processes instruction at the hardware level. So this shows how the CPU and the hardware, or the software and the hardware, or the hardware inside, connects to each other. So SAP consists of several essential components. The program counter, or the PC itself, tracks the address of the current instruction. The memory address register, or the MAR, selects memory locations. Random access memory, or everyone's favorite RAM, stores instruction and the data. The instruction register, or IR, holds the current instructions. The accumulator, A and B, registers store operands. The arithmetic logic unit, or ALU, performs calculations. And finally, the output register displays the final result. That's here. Here you go. Then, the instruction cycle follows a structured sequence: fetching the instruction from memory, decoding the opcode and operand, executing the operation through the ALU, and incrementing the program counter, or the PC, to proceed to the next instruction. SAP1, or Simple as Possible Computer 1, utilizes an 8-bit instruction format, where the upper 4 bits represent the next operation, or the operation code, and the lower 4 bits specify the memory address. So an example here, for us to be able to understand it. SAP1 can load two numeric values from memory, add them together using the ALU, and present the computed result through the output register. That is a simple representation of how that works. Okay, so finally, the final topic of this video and document is that programming, or SAP1 programming. So what does SAP mean? It's simple as possible. So the simple as possible programming involves writing simple machine level instructions that directly control hardware behavior. Each instruction consists of an opcode and memory address operand. Common instructions include LDA, or load accumulator, ADD, add accumulator, sub or subtract, out or output result, and finally HLT, which stands for halt execution. So a typical SAP1 program follows a logical sequence of loading data, performing computations, displaying output, and terminating execution. This low-level programming approach enhances understanding of memory addressing, data movement, and processor control signals. So a very simple program here is that LDA08, which means it's going to load the accumulator, add it as here, add the accumulator, and then out as the output result, and halt execution, which means to stop the execution. So it follows that sequential program, which load, add, out, and halt. So after it loaded something, it's gonna add, and it's gonna display the result, and then it's gonna stop the process. So this program loads two values from memory location 08 and 09, which here adds them together, outputs the results on the output, and halts the system, stops the system. Through such exercises, learners gain insight into instruction sequencing, hardware coordination, and fundamental computing logic. That is it, and here is a picture. So it's clear of how the CPU works here. Fetch, decode, registers, execute. That's a simple sequential CPU work. Then next is the evolution of CPU. Here's another Intel from 1970s up until modern multi-core. Then here's the overview of the GPU. It summarizes that it has 3D graphics, AI processing, and video rendering, which helps your computer and it benefits your computer very much. Then SAP operations are simple as possible operations, program counter, memory, output, instruction register, ALU, and the binary here. And this is going to be the output. Lastly, SAP1 programming, LDA08, add09, out, halt here, and this is the output. So that will be all. Thank you for listening. Again, my name is Clarence Sagayno. I'm from the SCP-41 from Santa Maria, Bulacan, PUP Santa Maria, Bulacan campus. And that will be all. Thank you.